with reference to the attachment of aluminium superstructures to a steel hull. A. Explain why it is not normal practice to join the two components using conventional welding techniques. B. State the particular problems associated with the aluminium superstructure where it is bonded to a steel hull. C. Outline the maintenance that should be carried out to ensure the continued structural integrity of the vessel. D. Sketch a typical transition joint that could be utilized to attach an aluminium superstructure to a steel hull. A. Conventional welding techniques are not normally used to join aluminium superstructures to steel hulls because of the different electrical properties of the two metals. Steel has a higher melting point than aluminium, so that when the two metals are welded together, the aluminium can melt before the steel, resulting in a weak joint. Additionally, steel is more prone to rust than aluminium, and the heat from welding can accelerate the corrosion process. B. The particular problems associated with an aluminium superstructure bonded to a steel hull include galvanic corrosion. This type of corrosion occurs when two dissimilar metals are in contact with each other in the presence of an electrolyte such as seawater. The electricity from the steel hull can flow to the aluminium superstructure, causing the aluminium to corrode. Stress corrosion cracking. This type of cracking can occur in aluminium alloys that are subjected to stress and a corrosive environment. The stress can come from the weight of the superstructure or from the waves and wind. Fatigue. Aluminium is more susceptible to fatigue than steel, so the superstructure is more likely to crack under repeated loading. C. The maintenance that should be carried out to ensure the continual structured integrity of the vessel includes regularly inspecting the joints between the superstructure and the hull for signs of corrosion or cracking, maintaining the protective coatings on both the steel and aluminium, monitoring the stress levels in the superstructure and taking steps to reduce them if necessary. D. Sketch of a typical transition joint. State, with reasons, a different welding, brazing, soldering process that is best suited to effect each of the following situations. A. Joining two lengths of aluminium bronze seawater pipe, both pipes having the same diameter. B. Attaching a stainless steel handrail to a steel hull. C. Reattach a section of broken flange on a cast iron pump casing. D. Attaching a brass flange onto a stainless steel pipe. E. Attaching a 1 mm steel section to a 10 mm thick deckhead plate. A. Joining two lengths of aluminium bronze seawater pipe, both pipes having the same diameter. The best process for this situation is gas tungsten arc welding, GTAW, also known as TIG welding. TIG welding is a precise and controlled process that is well suited for joining thin metals such as aluminium bronze. It is also resistant to corrosion, which is important for seawater pipes. B. Attaching a stainless steel handrail to a steel hull. The best process for this situation is shielded metal arc welding, SMAW, also known as stick welding. SMAW is a versatile process that can be used to join a variety of metals, including steel and stainless steel. It is also a relatively inexpensive and portable process, which makes it a good choice for shipboard repairs. C. Reattaching a section of broken flange on a cast iron pump casing. The best process for this situation is brazing. Brazing uses a filler metal that has a lower melting point than the base metals. This allows the filler metal to melt and flow into the joint without melting the base metals. Brazing is a good choice for cast iron because it is less likely to cause cracking. D. Attaching a brass flange onto a stainless steel pipe. The best process for this situation is silver soldering. Silver solder is a type of solder that has a high melting point and is very strong. It is a good choice for joining dissimilar metals such as brass and stainless steel. E. Attaching a 1 mm steel section to a 10 mm thick deckhead plate. The best process for this situation is laser beam welding. Laser beam welding is a high energy process that can create very strong and narrow welds. It is a good choice for this situation because it can weld the thin steel section to the thicker deckhead plate without melting too much of either metal. A. Outline 3 disadvantages of using aluminium in vessel construction. B. Outline 3 advantages of using steel in vessel construction. C. Outline 4 conditions necessary in the preparation of steel surfaces prior to painting to ensure a good surface finish. Disadvantages of using aluminium in vessel construction. Higher cost. Aluminium is generally more expensive than steel, which can be a major disadvantage for large vessels. Lower strength. Aluminium is not as strong as steel, so it may not be suitable for all applications. For example, it may not be strong enough to withstand the forces of heavy seas or ice. More difficult to weld. Aluminium can be more difficult to weld than steel, which can increase the cost and complexity of construction. Advantages of using steel in vessel construction. Lower cost. Steel is generally less expensive than aluminium, which can be a major advantage for large vessels. Higher strength. Steel is stronger than aluminium, so it is better suited for applications where strength is important. Easier to weld. Steel is easier to weld than aluminium, which can reduce the cost and complexity of construction. Conditions necessary for preparing steel surfaces prior to painting. Surface must be clean and free of dirt, grease and oil. This is essential for ensuring that the paint adheres properly to the steel. The surface must be rough enough to provide a good tooth or key for the paint. This can be achieved by sandblasting or other methods. Surface must be dry. Moisture can prevent the paint from adhering properly. The steel must be at the correct temperature. Painting should not be done if the steel is too hot or too cold. A. Describe the properties that make it suitable for each of the following. 1. Hull construction. 2. Mast construction. B. Explain its undesirable properties for the applications in Part A. C. Explain the safety considerations necessary when working with carbon fibre. A. Hull construction. High strength to weight ratio. Carbon fibre is incredibly strong for its weight, making it ideal for building lightweight hulls that can withstand the stress of waves and currents. This can improve a vessel's fuel efficiency and performance. Corrosion resistance. Carbon fibre is highly resistant to corrosion from saltwater and other marine environments, unlike metals like steel, which can rust and deteriorate. This reduces maintenance costs and extends the lifespan of the hull. Stiffness and dimensional stability. Carbon fibre composites have minimal thermal expansion and contraction, helping the hull maintain its shape and integrity even in changing temperatures. Mast construction. High stiffness and low weight. These properties allow for taller and lighter masts that can carry more sail area without bending excessively. This can improve a vessel's sailing performance and stability. Fatigue resistance. Carbon fibre masts can withstand repeated cycles of stress without breaking, making them ideal for long voyages and harsh conditions. Improved sail control. The stiffness of carbon fibre masts provides a more responsive feel to the sails, giving the crew greater control over the vessel. B. The undesirable properties of carbon fibre for marine applications. High cost. Carbon fibre is significantly more expensive than traditional materials like fiberglass or wood, making it a less economical choice for some applications. Brittle failure. While strong, carbon fibre can be brittle and prone to catastrophic failure if damaged. This can be a safety concern, especially for high-performance vessels. Repair difficulty. Repairing damage to carbon fibre can be complex and expensive, requiring specialised training and materials. Safety considerations when working with carbon fibre. Sharp fibres. Carbon fibres can be sharp and cause skin irritation or even puncture wounds if handled improperly. Proper personal protective equipment, PPE, like gloves and long sleeves, is essential when working with carbon fibre. Dust hazard. Cutting or sanding carbon fibre releases dust particles that can be harmful if inhaled. Proper ventilation and respiratory protection are necessary to avoid health risks. Galvanic corrosion. When combined with metals, carbon fibre can create galvanic corrosion which can damage both materials. Careful selection of compatible materials and proper insulation are necessary to prevent this. With reference to the manufacture of carbon fibre components. A. Describe each of the following processes and its advantages. 1. Vacuum bagging. 2. Autoclave curing. 3. Resin transfer moulding. B. List the type of component that each process described in Part A is best suited to. Here is a breakdown of each process. Vacuum bagging. The process. A dry fibre preform is placed in a mould and then covered with a vacuum bag. The air is evacuated from the bag, which applies pressure to the preform and forces the resin to flow through it. The part is then cured under heat. Advantages. Simple and relatively inexpensive process. Can be used with a wide variety of mould materials and shapes. Good for producing parts with a high fibre volume fraction. Disadvantages. Limited to parts with simple geometries. Voiding, which is air pockets, can be an issue, and not suitable for high performance applications. Autoclave curing process. The vacuum bagged part is placed in an autoclave, which is a pressure vessel that can be heated and pressurized. The pressure helps to consolidate the laminate and eliminate voids. Advantages: produces high quality parts with excellent surface finish and low void content. Suitable for complex geometries and high performance applications. Disadvantages: expensive process due to the high cost of autoclaves. Limited throughput due to the long cycle times. Not suitable for large parts. Resin transfer molding (RTM) process. The dry fiber preform is placed in a closed mold and then resin is injected into the mold under pressure. The part is then cured under heat. Advantages: can produce high quality parts with good surface finish and low void content. Faster cycle times than autoclave curing. Can be used for larger parts than vacuum bagging. Disadvantages: it's a more complex process than vacuum bagging, requires specialized molds and equipment, and not suitable for all geometries. With reference to carbon fiber, A. Describe how the base raw material is turned into a usable carbon fiber. B. Describe how the fibers produced in Part A are turned into a usable product. C. Explain how its internal structure gives it its unique strength properties. D. List 4 properties of carbon fiber that make it desirable for marine fabrication. A. Describing how the base raw material is turned into a usable carbon fiber. 1. Precursor selection. The first step is to choose the right precursor material, which is typically PAN, polyacrylonitrile. PAN is a synthetic polymer that can be converted into carbon fiber through a high temperature process. 2. Oxidation. The PAN precursor is then oxidized in air at temperatures between 200 and 400 Celsius. This process removes some of the hydrogen and nitrogen atoms from the PAN chains, making them more rigid and stable. 3. Carbonization. The oxidized PAN is then carbonized in an inert atmosphere at temperatures between 1000 and 2000 Celsius. This process dries off the remaining non-carbon atoms, leaving behind a highly ordered structure of carbon atoms. 4. Surface treatment. The carbon fibers are then treated with a sizing agent to improve their adhesion to resin and other materials. B. How the fibers produced in Part A are turned into a usable product. 1. Layup. The carbon fibers are arranged in a mold or on a mandrel in the desired shape of the final product. This process is called layup. 2. Resin infusion or impregnation. Resin is then infused or impregnated into the fibers. This can be done through vacuum bagging, autoclave curing, or other techniques. 3. Curing. The resin is then cured, typically under heat and pressure. This process converts the resin from a liquid to a solid, binding the fibers together and forming the final composite product. 4. Finishing. The cured product may then be machined, painted, or coated to meet the specific requirements of the application. C. How the internal structure of carbon fiber gives its unique strength properties. The unique strength of carbon fiber comes from its highly ordered internal structure. Each carbon fiber is made up of millions of carbon atoms arranged in a hexagonal lattice. This strong and stiff arrangement of atoms give carbon fibers a very high tensile strength, which is strength under pulling forces, and a high modulus of elasticity, resistance to deformation. In addition to its strong internal structure, carbon fibre is also very lightweight. This combination of high strength and low weight makes carbon fibre an ideal material for many marine applications where weight saving and high performance are essential. D. 4 properties of carbon fibre that make it desirable for marine fabrication. 1. High strength to weight ratio. Carbon fibre is incredibly strong for its weight, making it ideal for building lightweight hulls that can withstand the stress of waves and currents. This can improve a vessel's fuel efficiency and performance. 2. Corrosion resistance. Carbon fibre is highly resistant to corrosion from salt water and other marine environments, unlike metals like steel, which can rust and deteriorate. This reduces maintenance costs and extends the lifespan of the hull. 3. Stiffness and dimensional stability. Carbon fibre composites have minimal thermal expansion and contraction, helping the hull maintain its shape and integrity even in changing temperatures. 4. Fatigue resistance. Carbon fibre masts can withstand repeated cycles of stress without breaking, making them ideal for long voyages and harsh conditions. With reference to in-service defects found in glass reinforced plastic GRP hulls, A. State 3 possible causes of delamination. B. Describe 2 methods of detecting delamination in service. C. Describe 2 methods of repair to delamination on a sandwich construction hull. D. List 3 design problems that can lead to stress cracking. A. Causes of delamination. 1. Stress on the hull. Physical stress on the hull can cause the layers of fiberglass and resin to separate. This can happen due to impact, grounding, or overloading. 2. Water ingress. If water gets into the laminate, it can weaken the bond between the layers and lead to delamination. This can happen through cracks in the gel coat, poor sealing around fittings, or inadequate drainage. 3. Poor construction. Defects in the construction of the hull, such as voids in the laminate or improper curing of the resin, can also lead to delamination. B. Detecting delamination. 1. Tapping. Gently tapping on the hull with a mallet or other blunt object can produce a hollow sound if there is delamination beneath the surface. 2. Visual inspection. Looking for signs of cracking, bulging, or discoloration in the gel coat can also indicate delamination. C. Repairing delamination on a sandwich construction hull. 1. Vacuum injection. This technique involves injecting resin under pressure into the delaminated area to fill the voids and rebond the layers. 2. Grouting and relaminating. This method involves removing the damaged material, filling the delaminated area with epoxy grout, and then relaminating the surface. D. Design problems leading to stress cracking. 1. Sharp corners. Sharp corners in the hull design can create stress concentrations that make the material more susceptible to cracking. 2. Inadequate stiffening. If the hull is not properly stiffened, it can flex under load and develop cracks over time. 3. Discontinuities in the laminate. Holes, cutouts, or other discontinuities in the laminate can also create weak spots where cracks are more likely to occur. With reference to osmosis in glass reinforced plastic GRP hulls, A. Explain how osmosis may be detected in service. B. Explain why simply drying out the hull is not a cure for the effects of osmosis. C. Describe the full process for the treatment of a hull suffering from the effects of osmosis. A. How osmosis may be detected in service. Osmosis is a process where water diffuses through a semi-permeable membrane from a less concentrated solution to a more concentrated one. In the case of GRP hulls, the semi-permeable membrane is the gel coat, and the more concentrated solution is the seawater outside the hull. This can cause the gel coat to blister and delaminate. Ways to detect osmosis in service. 1. Visual inspection. Look for blisters, cracks, or changes in the colour or texture of the gel coat. 2. Tapping. Gently tap on the hull with a mallet or other blunt object. A hollow sound may indicate delamination beneath the surface. 3. Moisture meter. Use a moisture meter to measure the moisture content of the hull. This can be a more quantitative way to detect osmosis. B. Why simply drying out the hull is not a cure for the effects of osmosis. Simply drying out the hull will not cure the effects of osmosis because it does not address the underlying cause of the problem, which is the presence of water trapped within the laminate. Once water has entered the laminate, it can react with the resin and cause it to break down. Even if the hull is dried out, the damage has already been done, and the blisters and delamination will likely reappear. C. Full process for the treatment of a hull suffering from the effects of osmosis. The full process for treating a hull suffering from osmosis is a complex one and can vary depending on the severity of the damage. However, here are the general steps involved. 1. Cleaning and drying the hull. The hull must be thoroughly cleaned to remove any dirt, grime, or salt deposits. It should then be dried out completely, ideally using a combination of heat and ventilation. 2. Grinding. The blisters and any delaminated areas must be ground out to remove the damaged material. 3. Neutralizing the acids. The exposed laminate must be neutralized to remove any acidic salts that can cause further damage. 4. Filling and fairing. The ground out areas must be filled with a suitable epoxy filler and faired smooth. 5. Relaminating. A new layer of gel coat or epoxy resin must be applied to the repaired areas. 6. Painting. The hull may need to be repainted to restore its appearance and protect it from further damage. With reference to osmosis in glass reinforced plastic GRP hulls. A. Explain the process of osmosis and the method by which osmotic blisters occur in service. B. Describe a procedure for the local treatment of a single blister. A. How water diffuses through the gel coat. Water diffuses through the gel coat via a process called osmosis. Here are the steps involved in this process. 1. Concentration gradient. There is a higher concentration of salt molecules in the seawater surrounding the boat hull compared to the inside of the hull. This creates a concentration gradient. 2. Semi-permeable membrane. The gel coat acts as a semi-permeable membrane. This means that it allows water molecules to pass through, but it blocks the passage of salt molecules. 3. Diffusion. Water molecules move from the area of lower concentration, inside the hull, to the area of higher concentration, seawater, through the gel coat. This movement is driven by the natural tendency of systems to equalize concentrations. As water diffuses through the gel coat and into the laminate, it can cause the resin in the laminate to break down. This breakdown process releases gases which can create pockets or voids within the laminate. These pockets can eventually grow large enough to form blisters on the hull surface. B. A procedure for the local treatment of a single blister. 1. Pierce and drain the blister, taking safety precautions. 2. Sand back to clean laminate. 3. Wash, rinse and scrub clean. 4. After drying, clean with acetone. 5. Mix and apply epoxy resin and silica filler. 6. Sanding and fairing. 7. Paint to finish. With reference to osmosis in glass reinforced plastic GRP hulls. A. Explain the process of osmosis and the method by which osmotic blisters occur in service. B. Describe a procedure for the local treatment of a single blister. A. How water diffuses through the gel coat. Water diffuses through the gel coat via a process called osmosis. Here are the steps involved in this process. 1. Concentration gradient. There is a higher concentration of salt molecules in the seawater surrounding the boat hull compared to the inside of the hull. This creates a concentration gradient. 2. Semi-permeable membrane. The gel coat acts as a semi-permeable membrane. This means that it allows water molecules to pass through, but it blocks the passage of salt molecules. 3. Diffusion. Water molecules move from the area of lower concentration, inside the hull, to the area of higher concentration, seawater, through the gel coat. This movement is driven by the natural tendency of systems to equalize concentrations. As water diffuses through the gel coat and into the laminate, it can cause the resin in the laminate to break down. This breakdown process releases gases which can create pockets or voids within the laminate. These pockets can eventually grow large enough to form blisters on the hull surface. B. A procedure for the local treatment of a single blister. 1. Pierce and drain the blister, taking safety precautions. 2. Sand back to clean laminate. 3. Wash, rinse and scrub clean. 4. After drying, clean with acetone. 5. Mix and apply epoxy resin and silica filler. 6. Sanding and fairing. 7. Paint to finish. With reference to glass reinforced plastic GRP hulls. A. State 3 causes for each of the following defects to occur. 1. Delamination. 2. Osmotic blisters. 3. Stress cracking. B. State the part of the underwater section of the hull on which osmotic blisters most commonly occur. Causes of defects. A. 1. Delamination. 1. Improper resin mixing. Incorrect resin to hardener ratio can lead to incomplete curing, weakening the bond between layers. 2. Insufficient resin application. Not enough resin between layers can create air pockets and weak bonds. 3. Contamination. Dirt, grease or moisture trapped between layers can prevent proper adhesion. 4. Uneven pressure during layup. Inconsistent pressure can lead to voids and weak areas. 5. Excessive sanding. Removing too much material can thin layers and reduce overall strength. 2. Osmotic blisters. 1. Water permeation. Diffusion of water molecules through the GRP laminate. 2. Presence of salts. Undissolved salts in the water attract more water, creating osmotic pressure. 3. Imperfect laminate. Micro cracks, voids, or poor adhesion points allow water ingress. 4. Lack of protective barrier. Inadequate gel coat or anti-osmosis coating allows water contact. 5. Temperature cycling. Expansion and contraction due to temperature changes can stress the laminate, exacerbating existing weaknesses. 3. Stress cracking. 1. Mechanical overload. Excessive loads exceeding the design limits of the hull. 2. Impact damage. Punctures, dents, or other forceful impacts can initiate cracks. 3. Poor design. Stress concentrations due to sharp corners, inadequate reinforcement, or improper load distribution. 4. Fatigue. Repeated loading and unloading cycles can weaken the material and lead to crack propagation. 5. Environmental factors. UV exposure, chemical attack, or temperature extremes can degrade the mechanical properties of GRP. B. Osmotic blister location. Osmotic blisters most commonly occur on the underwater sections of the hull exposed to prolonged water contact. These include the keel, bilge areas, garboards, and lower portions of the transom. These areas experience constant immersion and higher salt concentrations, making them more susceptible to water permeation and osmotic pressure buildup. With reference to the production of glass reinforced plastic GRP hulls. A. Describe the process of resin infusion moulding for the production of a hull. B. State the advantages of resin infusion moulding with respect to traditional methods of construction. C. Explain how this process can virtually eliminate the onset of osmosis in the hull. A. Preparation. The first step is to prepare the mould. This typically involves cleaning and waxing the mould to ensure a smooth finish. Layup. The dry glass fibre reinforcements are then placed in the mould. These reinforcements can be in the form of mats, woven fabric, or unidirectional tapes. Resin infusion. The resin is then infused into the dry glass fibres. This can be done by gravity, but is more common to use a vacuum to draw the resin through the fibres. Curing. Once the resin is infused, the mould is sealed and the resin is allowed to cure. This is typically done at an elevated temperature. Finishing. Once the resin is cured, the part can be removed from the mould and any finishing work can be done. This may include sanding, painting, or adding hardware. Resin infusion moulding has several advantages over traditional methods of GRP hull construction, such as hand layup and spray up. These advantages include higher fibre to resin ratio. Resin infusion moulding typically results in a higher fibre to resin ratio than other methods. This means that the hulls are stronger and lighter. Reduced void content. Resin infusion moulding also reduces the void content in the laminate. Voids are air pockets that can weaken the laminates and make it more susceptible to water absorption. Improved surface finish. Resin infusion molding typically produces a better surface finish than other methods. This is because the resin is evenly distributed throughout the laminate. Reduced emissions. Resin infusion molding is a closed mold process, which means there are fewer emissions of volatile organic compounds, VOCs, into the atmosphere. Resin infusion molding can also virtually eliminate the onset of osmosis in the hull. Osmosis is a process that can cause blisters to form on the surface of the hull. It is caused by the diffusion of water through the hull and into the laminate. Resin infusion molding creates a denser laminate with fewer voids, which makes it less susceptible to osmosis. Overall, resin infusion molding is a versatile and efficient process for producing high-quality GRP hulls. It is a good choice for boat builders who are looking for strong, lightweight and durable hulls. With reference to the production of glass reinforced plastic GRP hulls, A. Outline the properties of glass fibre and resin that make them suitable for the construction of a hull. B. Describe the traditional method for the layup of a GRP hull. C. List 4 disadvantages of GRP hulls in service. A. Material properties. Glass fibre. High strength to weight ratio. Lightweight yet strong, providing good overall hull strength without excessive weight. Corrosion resistance. Resists salt water and other harsh marine environments. Ideal for boat hulls. Dimensional stability. Maintains shape well, minimizing warping or deformation. Electrical insulation. Non-conductive, preventing electrolysis issues between hull and electrical components. Resin. Binds and protects fibres, creates a strong composite material by holding fibres together and providing surface protection. Watertight. Forms a continuous barrier against water ingress, crucial for hull integrity. Curable. Transforms from liquid to solid, allowing for shaping and moulding during construction. Variable properties. Different resin types offer varying flexibility, rigidity, and chemical resistance to suit specific hull needs. B. Traditional layup method. 1. Mould preparation. A polished mould with the desired hull shape is prepared. 2. Gel coat application. A thin layer of pigmented gel coat is sprayed onto the mould for a smooth, protective outer surface. 3. Reinforcement layer. Chopped strand mat, CSM, or woven roving fiberglass fabrics are applied and saturated with resin, building initial thickness and strength. 4. Additional layers. Further layers of different fabric types and resin are added based on design requirements, varying thickness and stiffness in different areas. 5. Consolidation. Techniques like rollers, vacuum bagging, or hand pressure ensure proper resin distribution and eliminate air pockets. 6. Curing. The resin is allowed to cure and harden, typically at room temperature or with controlled heat. 7. Mould release. The cured hull is carefully removed from the mould for finishing and fitting. C. Disadvantages of GRP hulls. 1. Osmosis susceptibility. Can be prone to osmotic blisters if water permeates through the laminate and encounters salts, leading to structural damage. 2. Stress cracking. Susceptible to cracking under high loads or stress, especially if design or construction isn't robust enough. 3. Fire resistance. Not inherently fire resistant, requiring additional fireproofing measures for safety. 4. Repair challenges. Complex repairs require skilled technicians and specific materials, sometimes needing professional intervention. While GRP offers advantages in cost, versatility, and weight savings, these disadvantages in service need to be considered and mitigated through proper maintenance, design, and construction practices. With reference to root whitening in GRP hull construction. A. Explain the term root whitening, stating where it is most likely to occur. B. Explain 2 possible reasons why this may happen. C. State 2 possible actions that could be taken if it is discovered. Root whitening refers to a phenomenon in GRP hulls where the glass fibres lose their transparency and appear white near the point they are bonded to the resin. This typically occurs at the base or the root of the fibres, close to the inner surface of the hull. Possible reasons. 1. Hydrolysis. This involves the breakdown of the glass fibres due to prolonged exposure to moisture. Water molecules react with the silica in the fibres, weakening the bond and causing whitening. This is more likely in areas with poor resin coverage or micro cracks allowing water ingress. Stress concentration. When the hull experiences excessive mechanical stress, localized pressure can cause damage to the glass fibers at their attachment points to the resin. This can manifest as fiber microfractures and whitening, particularly in areas with sharp corners or design stress points. C. Possible actions. 1. Inspection and assessment. The extent of the whitening and potential structural impact should be thoroughly evaluated. This may involve ultrasound testing or core samples to assess the internal condition of the hull. 2. Repair or corrective measures. Depending on the severity and location, various repair options can be considered. Minor cases might involve localized sanding and relamination with fresh resin. In more extensive cases, structural reinforcement or even hull sections replacement might be necessary. It's crucial to act promptly upon discovering root whitening, as it can indicate underlying issues affecting the hull's integrity and safety. Addressing these issues early can prevent further damage and potentially costly repairs in the long run. Additional notes. Root whitening might not always be readily visible from the outside of the hull and might require specialized inspection techniques for detection. The best course of action for addressing root whitening depends on various factors, including the degree of severity, specific location, and overall boat construction.